Yes, I'm a physicist working in quantum optics, quantum physics. I started my career long ago, as you can see from my face. I was lucky to start when the laser was invented, and so all my career has been based on experiments where I have been using the laser as a source and as a way to manipulate atomic systems. So it's a fantastic new piece of equipment that we have now, which allow us to manipulate single atoms, single particles, to prepare sources which produce single photons. And by having these elementary systems interact with each other, we can do things that we could not even dream about when I started my career as a scientist in the 1960s. So, and I have been also fortunate not only to do experiments which I like, but also to witness all what my colleagues have been doing during that time in different areas, most of them using lasers also to achieve fantastic things. So I'm ready to talk about that, and I think it's a fascinating domain of research which still has a lot of things to deliver in the future. It's very difficult to explain because it's counterintuitive. We live in a world which is made of a huge number of particles. Each piece of matter that you see contains billions and billions and billions of atoms. And in this macroscopic world, nature behaves in a way for which we have intuition, because we see it every day and we have to adapt to the world. At the atomic level, physics obeys to laws which are not the ones that we see, so it looks strange, but it's the way it is. We have one principle in quantum physics is the principle of state superposition, the fact that before you perform any measurement, a system can exist in different classical states which seems to be incompatible with each other. An atom can be at different places at once. A photon can have different polarization at once. What it means is difficult to grasp with a classical mindset, but and there are different ways to see that. For example, to say that a particle can be at different places means that it has a wave character. A wave is something which occupies all the space which is given to it. So an electron in an atom can be at any place around the core, around the nucleus of the atom. And so you can say it by saying that it's in state superposition, but you can also say it by saying that in fact there is an electron cloud surrounding the atom, and this is the wave aspect of this kind of physics. So it looks strange for someone who has no training in this field, but the mathematics is quite simple. It's expressed in mathematical terms, in mathematical formalism, which is, I think, rather easy to grasp, not for a small kid, but I think for a student who has some mathematical training at the end of high school. It's possible to explain what's going on in the microscopic world. It's still strange because we don't have normal intuition for that. But you can gain a kind of mathematical intuition. You can understand what will happen when you do an experiment. And this is what I call the intuition of a physicist. Oh, that's a way of, you can think of it as you want. It's before you perform a measurement, the only thing you can say is that there is a probability to find it here or there if you perform a measurement. And just after the measurement, you know where it is. There's a place where you have found it during the measurement. So what lies behind that is a fundamental property of the world at the micro scale, which is undeterminism. You cannot, there is a part of chance, a part of luck in the microscopic world. You can only, it's a probabilistic world. Even if you do the same experiment twice, starting with the same initial conditions, this is when you will make a measurement after that, you will find you may find different results. So there is an intrinsic undeterminism, an intrinsic randomness in quantum physics, which is very different from what classical physics was about. Until the end of the 19th century, classical physics was deterministic. Laplace was a famous astronomer and mathematician at the beginning of the 19th century, said, if you give me the position and the velocities of all the atoms in the universe, I could tell the future. I could tell what will happen in the future. So this was determinism. Of course, it's impossible, but it was impossible for practical reasons. In quantum physics, it's impossible not for practical reasons. It's just impossible, period, because classical physics is not deterministic. And this is a very deep idea that a lot of famous physicists did not like. Einstein didn't like that. And so Einstein, in this aspect, in this way of explaining the world, was a classical physicist. In spite of the fact that he revolutionized everything with his theory of relativity and his general theory of relativity, and also his understanding of the early quantum theory, he was a classical physicist because he could not accept the idea that there was a part of chance in anything which happens in the micro world. But this is the way it is, and if you try to build a theory which gets rid of this randomness, you get immediately inconsistencies, and all what has been done since 1 century all vindicates this fact that quantum physics is random at the heart. In fact, everything works under the same set of rules because, of course, we are made of atoms. All matters around us is made of atoms. So the question is a good question, but we have to understand why we don't see that at the macro scale. And the reason is that we look at large ensembles, and so we have statistical effects which veil the quantumness, the fact that there is some randomness. If you have random events happening in the micro world, at the big scale, what you lose is a statistical average of all these quantum phenomena. So that's one way of looking at things. Another way is the fact is what we call decoherence. This randomness, the fact that matter is made of waves. Waves have a coherent feature. They all oscillate. Two waves which have the same phase oscillate together, and this gives rise to interference effects. When the crest of the wave come together at the same time, you have a maximum. When one wave is at the maximum and the other at the minimum, they cancel each other, and you have a minimum. And these phenomena are very sensitive to phase. To the phase coherence, to the fact that there is a well-defined difference of phase between two waves. But these phases are very fragile, and as soon as a quantum system, an atom, is connected to an environment made of a large number of atoms, all this phase coherence vanishes because it's just lost in the environment, and this is called decoherence. So if you want to see the quantum effects, what you have to do is to focus on one atom, on a small number of atoms, and make sure that they don't interact with the environment. Because if they interact with the huge number of atoms that you have around, this very fragile coherence will be lost in the middle of everything, and you will see only average effects which restore the classical world. So the quantumness is there, but it is mixed with the environment very quickly, and that's what makes the world appear classical. When you lose all the information which is contained in the phase relationship between the different parts, and then you lose all this and you get only classical effects, and you can show also mathematically that the limit when you lose this quantum coherence is the classical world as we know it, and the classical laws as we see them. You retrieve Newton's law, the classical Newton's law, even if each atom behaves in a way which is strange compared to that. It means that you have to get rid of all the perturbations which, as I just said, hide, veil this quantumness. So you have to make, if you want to see the quantum world, the intrinsic quantum world, which gives us the very simple effects, you have to get rid of all the complications which are related to the fact that these small systems are very easily perturbed. So, for example, a photon is a very elusive particle. A photon flies at the speed of light. So if you leave a photon in free space, in a nanosecond it will disappear from your experimental setup. You have a setup which is 30 centimeters in size. Speed of light in 30 centimeters takes 1 nanosecond, 1 billionth of a second, so it's lost. So the first thing we do is that we trap the light. We put mirrors and we make the photon bounce between the mirrors. But the difficulty there is that at each bounce you have a strong probability to lose the photon because of absorption in the walls or scattering due to imperfection of the walls. So you have to have extremely good mirrors. The mirrors that we were able to produce were keeping the photon for, let's say, 1/10 of a second, which looks very short time for us, but it's a very long time for a photon and for an atom. You have to think that the atomic processes occur at a time scale of femtosecond, nanosecond, and so a second is a very long time. But on the other hand, for a photon to stay for a second between mirrors, it means that it has to bounce billions of times between the mirrors. And so the mirrors have to be such that the photon is not, has only one chance over a billion to be lost at each bounce. And these are extremely good mirrors. So there's a lot of technology involved with that. Then you have to get a single atom. So to get a single atom is also difficult because in a piece of matter you have 10 to the 20, 10 to the 22 atoms. So you have to evaporate to get a gas, a very dilute gas in a good vacuum, an atomic beam, and have a very precise laser which will excite only one atom at a time. And then you have to have this atom interact with the system. That was a technology when I started and when I did the experiment for which the Nobel Prize was given. Now people do much better. In my group we do much better. Not only we can have a single atom flying in a cavity, but we can trap the atom and keep it still. And we use what is called optical tweezers. That is, we focus a laser beam and the atoms are attracted at the focus of the laser beam, and it's like you had tweezers and you can move the atom, put it where you want and keep it there. And we can do experiments that we could not do even 10 or 15 years ago. And this is the progress of this kind of physics. And now we can do things which go much beyond what we did at that time. So we use the technology, especially in our case in optical technology, to be able to isolate single atoms and single photons and see what happens when they interact. We can also bring two atoms close together at a well-defined distance and see how they can exchange energy, how they speak to each other in quantum ways, using the laws of quantum physics. And for that we use special atoms. The last piece of information that you need to understand what we are doing, we use Rydberg atoms. A Rydberg atom is an atom in which an electron is excited to a very large orbit. It's thousands of times bigger than an ordinary atom. And the electron is so weakly bound to the nucleus that it's very sensitive to all kinds of perturbation. When you have two atoms, usually when you have two atoms at a distance of a few micrometers, it's a huge distance, they don't see each other. But if they are Rydberg atoms, they feel each other even if the distance is thousands of times, 10,000 of times larger than for ordinary atoms. And so you can, in fact, observe quantum interaction between atoms at large distances. And these are atoms for which you control not only the distance and the position, but you also control the quantum state in which they are. You can excite them in one very excited state, or in another one is slightly more excited, and see how they go from one state to the other, exchanging microwave photons. And so it's the game becomes more and more precise, but also more and more complicated because you can add atoms and see what happens if you don't have only two atoms but an array of atoms, and it can be a one-dimensional array or a two-dimensional array or a three-dimensional array. And then what you do is in fact some kind of artificial matter. In ordinary matters, atoms are at 1 or 2 angstroms from each other. In the kind of matter I'm talking about, atoms are at several micrometers from each other. So it's very dilute matter, but it's ordered like a crystal, and looking at the interaction between these atoms can provide very useful information about quantum processes, but also can allow us to synthesize new materials, artificial materials, which may have a counterpart in the real world. So this is called quantum simulation. And my group, I am now just witnessing what we are doing because I'm no longer actively doing my own research, but this is the offspring of the research I've been doing all my life, and I think it's fascinating. Okay, I can give you an example. About 40 years ago, physicists have discovered what is called high TC superconductivity, which is the property that matter has to conduct electricity without losses, without resistance. It was known for more than a century that this exists, but at ultra low temperature. Some metals, large number of metals, when you cool them down to near to absolute zero temperature, start to be superconducting. And this is a technology which is very useful. For example, it's useful to carry huge, very large intensity of currents in the magnets of the LHC, of the magnets of accelerators, and also in a more mundane way, in the magnets of magnetic resonance imaging. When you go to hospital, if you are going to be submitted to MRI, you are inserted into a big machine, and in the big machine you have wires that you don't see, and these wires, a very high current is circulating, and it's a superconducting current, and in this big surrounding you have in fact a kind of dewar which holds liquid helium, very, very low temperature. So it's very expensive, and this is why these machines, there are not so many machines in the world like that. It's very expensive, and you cannot do that to transport electricity everywhere. Then 40 years ago, it has been discovered that you have other kind of other kind of superconductors which do not require such a low temperature. They have been called high critical temperature superconductors. You still need to cool to not 273 degrees below zero, but let's say 150 degrees below zero. It's still very, very cold, but it means that you have some features in matter. These structures are very subtle forms of ceramics, which have a different structure than ordinary metals, but you see that if you change the structure of matter, you can find new properties, like being able to carry electric currents without losses. The dream is to be able to synthesize materials which will carry electricity without losses at room temperature. If you can do that, then you will save a lot of energy, because you would carry electricity over thousands of kilometers without heating the wires. In fact, usually 20 to 30% of the electricity is lost just because of this heating. So people are looking for that, but it's very difficult to understand why these structures, why these new materials are able to do that, and they are able to do that very often under very special circumstances, very high pressure, for instance. So you have to play with the structures, and the kind of simulation I was talking about is a way to do that. You can arrange atoms in such a way that in these artificial structures you can understand how the transport properties of the material will allow for this to happen at high temperature. So there are people working around these ideas, and there are some progress. It's still not sure, but if this happens, it will be a huge, very important result, practical result. If we get materials, if you are able to synthesize materials which do that. Another domain in which this kind of process is interesting is chemistry, especially the pharmaceutical industry. You can think of synthesize new molecules which might have properties interesting to cure some disease, and so people are putting a lot of hope in these quantum simulations to try to synthesize and design new materials. That's one way. And another way is just to understand the complexity of the quantum world, to see how the particles are able to talk to each other with these quantum properties, and this is the field of quantum information. Well, first of all, of course, you can you can expect when you have achieved something which attracted the interest of your community. And when we were able with my group to show these quantum effects and to show that we had the building blocks for quantum information, this happened at the beginning of the year 2000, 2006, 2007. I was invited to a lot of meetings and conferences, and I could dream that the Nobel Prize could come, but it's always for each scientist, I would say now, there is a lot of a matter of luck in that, because we are a big community. There are thousands of researchers working in these areas, and there are, let's say, tens of very active and very productive groups, and who is picked to get a Nobel Prize. First of all, the topic has to be chosen by the Nobel Committee, and there are many topics beyond quantum optics which are worthwhile being given prizes. And even in the field I am working on, there are 6, 7, 8, 10 groups, I don't know, who are competing, most often in a friendly way, but it's a very competitive way. So I prefer not to think about the Nobel Prize before. To be frank, I was giving myself a 10% chance to get a Nobel Prize one day, but you never know which year, and you don't know whether it will happen or not, and you better not think about that, because it will not, for a lot of people who deserve it as much as anyone, as I did or other people did, you cannot count on that. And I think the people who are really each year wondering to know whether they will get it or not have become very nervous and very unhappy, because very often they are disappointed. So I tried, philosophically, I tried not to think about that. First of all, I did not think at all about that until maybe 6 or 7 years before it was given, and even then I tried not to think. Now when it happens, it's a big shock, because then you understand that suddenly you will be projected in the front line, and you will have to defend science and to defend the values of science and to defend the importance of science in the society, in the political world too, because I think a lot of politicians don't understand. Of course, they don't understand, but even often they don't understand the value of it, and they tend to dismiss it compared to other problems they have in mind. And they don't understand, I think, an important point, which goes even beyond science, the fact that education and science are the most important things for the future of a country, the future of society. We have to solve a lot of problems, challenging problems that we are facing now. Some of these problems have been created by science, but this is a paradox, but that's the way society and humanity works. So, but we have to get good scientists, and for that we need a good education. Not only a good education to have a reservoir from which good scientists will emerge, but also because we need all society to understand that science is important, and that science has values which are in danger now because of a lot of things like people who deny the value of science, people who plot theories and in French we say complotism, conspiracy theories.
Yeah, misinformation.
Misinformation, fake news, alternative facts and alternative truths, and all these things which are conspiring to dissolve the value of science in society. So, and this was already well felt 10 years ago, and even before the COVID, and even before for example, the climate change crisis started long ago, and this is an issue in which science should play a very important role. Yeah, but you are right, there is a conflict, a time conflict between the short time scale of politics and the long time scale of science. In fact, the basic, I was talking to you about the laser. The idea of the laser, the first idea of the laser emerged with Einstein's work when he discovered what is called stimulated emission, the fact that atoms can cooperate to emit together a light beam which has very special properties, very different from the one you have with ordinary light. But this was just a theoretical idea of Einstein. It took 50 years before the first laser was invented after that, and then it took another 50 years before all the application of lasers that we know today came to fruition. So it's a huge time scale, and of course politicians cannot worry about that. So, but I think, so it means that politicians should understand that science is a part of culture, and that culture is a fundamental aspiration of human mind, and that apart from their interest for short-term results, they should be able to promote these long-term projects. And there have been times in civilization where this was accepted. When the pharaoh built the pyramids, to build the pyramid took a century, and the pharaoh died before that, and the next pharaoh went on. So there are some long-term aspirations. Then at that time it was religious and mythical, and I think science should be understood in the same way. We need to develop science without just focusing on short-term results, because if we do that, for example, if somebody had been asking in 1950s, we need a laser beam doing this and that, and to start from scratch, no, but it would have been impossible. To give another example, when the COVID came and we had to find a vaccine, if no research had been done before about RNA messenger, it would have been an impossible task. Nobody would know in which direction to go. So the basic science is a kind of background on which application will grow, but you never know which part of the background will be used for the application. You just need to nurture the background all the time by doing basic science. And this is awfully difficult to make scientists understand. I think politicians understand when the big project is good for their ego, is good for their reputation when they compete with others. For example, the LHC, the big accelerators, they cost a lot of money, but the countries who contribute to that have the feeling that it contributes also to their exposure, to their reputation, and it's a part of the power game to be part of this big project. And this has been always the case. When in the 18th century, the King of France or the King of England paid for expedition like the Cook, the Cook voyages around the world, or La Pérouse going around the world. They spend a lot of money because it was part of the reputation of the country to participate to something which, from the start, did not provide any goods, any marketable products. And so I think politicians have to understand that, and usually they don't, because they are not statesmen, they are just small politicians. Unfortunately, the only countries in the world in which this can happen are countries which are not democratic, because then the leader can see can see the future over 10, 20 years, and so it's like what China is doing. So I don't think it's a solution. It's not good because science needs also freedom. So these people have the possibility to stay in power a lot, so to think about the future, but they don't provide the context, the freedom of speech, the freedom of thought, which is also essential to nurture big discoveries. So it's a very complicated situation. But beyond that, the other problem, which is also a very long-term project, I think education is in a very bad shape everywhere in the world and in Europe, and in France in particular. The level of education is going down. The students know much less than they used to know 20 or 30 years ago. We have to resolve this problem. But even if you put a lot of money in that, the reward will come within 10 or 15 years. It's a long-term project. It will not change from one year to the next. So politicians don't care. I am very happy to be in this jury because it gives me the opportunity to have a look at the science in Spain. And I'm very impressed by the level of the science I see now, and I know that it comes from very far, that Spain, in fact Spain became a country which is very productive in science only 20 or 30 years ago after the end of the Franco time, during which it was completely cut from the rest of the research world. So it has made a lot of progress, and it's very impressive to see in the field. I am in the jury of basic science, to see in the field of physics, chemistry, mathematics, the science of information. They are very, very good people, and so it gives me a kind of window in which I can see science in Spain. And I know that it's a prize which is very well known and appreciated in Spain as a prize which recognizes the evolution of science and the competition between Spanish scientists. So I think it's in this way I think it's very positive. I would say we are living to you a very complicated world with a lot of problems, and only scientists and engineers can, and people who know how to think deeply about questions can help to solve. So it's a big challenge for the future generations, and the way to address this challenge, you have to enter into this field one way or the other. And I think the only way to enter into it is to have a passion for one topic, whether it is physics, or material sciences, or biology, or brain, the study of the brain, or astronomy or astrophysics. You have to have a passion for one field and try to get the best, to become the best possible in the field you have a passion for. And there are a lot of parameters, a lot of things that you cannot control, which will come, of course, become very important. One is, most of it is luck. You have to be lucky to enter in a field which is promising. So it's not only luck, you have to feel that, to have the intuition that in this field great things will happen. And this intuition is not very complicated. If I started now, I know that, for example, to study the brain, how the brain works and the connection between the brain and all kind of manipulation of information is very important. So the connection between the functioning of the brain, artificial intelligence and so on is a fascinating topic. If you look outside at the universe, the search for exoplanets and the fact that the technology will allow us to find out whether there is life at billions of light years away from the Earth is also a fascinating topic. And of course it's not, you will not go there, we never go there, so we never gain anything material about that, but I think it's something which is worth looking for. And I could go on and go on. The unification of gravitation with quantum theory, which is also a very fascinating field. But of course I'm talking about things in which physics is important. But I know that there are similar ideas, similar topics possible in biology. And again, in my case, a big luck was to come at the time when the laser was coming on the stage.